In this video we're going to be looking at the inverting amplifier using a single op-amp. So in this configuration we've got our inverting, I've drawn it at the top this time, and non-inverting inputs, and we've got our output. And what we do is we apply negative feedback, as we saw in the last video, by connecting a resistor in the feedback path. So this becomes negative feedback, negative because it goes to the inverting input, and therefore with another resistor there in series with our input voltage, a fraction of our output is applied to the input which opposes it, so we get all those benefits that we saw from negative feedback. Alright, increased linearity, increased bandwidth and so forth. And we are going to ground our non-inverting terminal here. No, you don't have to, but this is the normal configuration for a non-inverting amplifier. Sorry, an inverting amplifier. These two resistors I normally call RF, the resistor in the feedback network. Right, so basically the circuit between the output and the input in that feedback path, and then RI for the input resistance. Now, in order to determine what the gain would be for this particular circuit, I'm interested here in not AOL, because I can get that from a data sheet or perhaps even attempt to measure it, but the closed loop gain. Right, that's what I am interested for this particular circuit, because I'm designing an amplifier. I obviously want to know what is the amplifier's value. So we start with the analysis of this circuit. So current through that resistor there, so through our input resistor, I will be equal to the voltage in, and I'm going to call this node here Vn for voltage at the input to our negative feedback terminal, or the inverting terminal. So Vn minus Vn, voltage drop across this resistor, divided by the value of that resistor will give us the current through it, and conversely the current here, IF, will be equal to the voltage drop across that resistor, so V out minus, Vin minus V out, Vn, not Vn, Vn minus V out over Rf. So that will give us the two currents flowing here. From Kirchhoff's current law, we know that the total current entering this node must be the sum of all the currents exiting it. So we know that II will be equal to IF plus IN. It's that current there. Now, from the ideal approximations we've made, that we saw in an earlier video, IN is equal to 0 amps. Okay, so there's actually no current flow there. So if IN equals 0 in the ideal case, II will be equal to IF. So all the current is flowing through the resistors to the output. Alright, furthermore, we know that if there is we assume the virtual short between these two terminals, so that the voltages between them have to be equal. Alright, if we come back to our circuit, we note that we're going to have 0 volts at Vp, so Vp has to equal Vn using the virtual short analogy. Therefore Vn also equals 0. Substituting these values and what we know from the ideal approximations, we see we get, just using these equations here, Vn minus Vn over Ri will equal to Vn minus V out over Rf, where that's 0, so therefore we get Vn over Ri is equal to minus V out over Rf. If we then rearrange this expression so that we get our equation for gain, so AVCL, the closed loop voltage gain, is equal to V out over V in. It's the standard equation for gain, which in this case will be equal to minus RF over RI, just by rearranging this equation above. So the analysis of our inverting amplifier is nothing more than looking at the currents through the resistors, taking into account Kirchhoff's current law, applying the approximations. So apply the ideal approximations, rearrange into a form for gain, and you'll come up with an expression based on the resistors will give you the closed loop voltage gain for the inverting amplifier.